Ladies and gentlemen, welcome to the first session of this afternoon. The speaker is Professor Altangerel from the German Mongolian Institute for Resources and Technologies. He is a well-known expert of variational calculus, and he will talk about quasi-variational inequalities. Let's welcome him.
Okay, thank you for nice introduction. My name is Altangerel. I am professor of mathematics at the German Mongolian Institute for Resource and Technology, and our university was established in 2013 as the youngest state university of Mongolia in cooperation with German and Mongolian government. Currently also all bachelor and master study programs are internationally accredited, and also we have some uniqueness at our university, such as instruction languages, English, and also I am representing Mongolian Mathematical Society, and this society was established almost 30 years ago, but 2 years ago, we became a member of International Mathematical Union, and also try to develop our cooperation, international cooperation with other mathematical community. And also thank you to organizers of this conference for the invitation, and also giving me opportunity also to participate this very nice conference. I am first time in this conference, and hopefully there's more delegates from Mongolia will also participate in this conference next time. And my topic is about quasi-variational inequalities. The talk consists of mainly 3 parts. The first one is about brief introduction about the quasi-variational inequalities. And in the second part, I will share some recent results on this continuous and discrete time models to solve quasi-variational inequalities. And the last part devotes to the actually originally very close connection to my PhD thesis from the Lkhamsuren University of Technology almost 19 years ago, and during this time also my thesis deals with the construction of gap function based on the conjugate duality for variational inequalities equilibrium problems, and during this time is also not so clear in how this approach can be extended to the quasi-variational inequalities, and also because of this feasible set depends on the variable. And there are some challenging issues, and then also I will try to explain. And then also recently, the so-called the quasi-equilibrium problem, which is the extension of the models, is also pay more attention on this direction, and also developing some existing results, and also gap function, and so on. Okay, then I will switch to the problem formulation. Okay, we consider the Hilbert space with the inner product and the topology induced by this norm, and also we consider nonlinear mapping, and also we have the following set-valued mapping K, such that Kx is non-empty closed convex values for each x. Then quasi-variational inequality consists in finding the vector element x from this kx, satisfying this condition for all y from the kx. And also you can see also this the k now this nothing constant set is here. We have this set valued mapping, and this is also some difficulties how this algorithms can be developed and so on. And then also I can mention some special cases, and also if we have instead of kx we have just the constant set, then it will be reduced to the classical variational inequality consists in finding vector x from this set satisfying this condition. And also it is well known that if you consider, for instance, Nash equilibrium problem, if we aim to solve Nash equilibrium problem, there's one approach to solve such kind of problem is also it will be reduced to the variational inequality, and also this 2 volumes of monograph by Pacchini and Kansov, this well known, and also from the theoretical perspective and also numerical algorithms, and next one is, of course, if you can see the Euclidean finite dimensional space, and K is non-negative artant, then this problem will be reduced to the so-called the complementary problem, then finding X and satisfying this condition, and K star is here the Fowler cone defined by as follows. And of course, if K is the Rn, then it will be reduced to the system of non-linear equations. Okay, this means we can say that also the quasi-variational liquidity is also very comprehensive also approach, the extending, generalizing some existing models. And originally, also quasi-variational inequality was introduced by Binzorsen in 1973 in the impulse control problems, which is very close connection to the partial differential equations originally, and then later also this model was discussed also in finite dimensional space and in Hilbert space, and of course have been the powerful tool for describing a wide range of complex equilibrium situations, and also when it is well known that this quasi-variational very close connection to the generalized Nash games, and also the Professor Fang and Fukushima also have publication also this connection between quasi-variational inequality and also multi-leader follower games, and there are many applications also related to economics, finance, also mechanics and engineering, traffic network, image illustration, and transportation network. This means also this also the reason why we need to investigate such kind of problem. And as I already mentioned, also somehow because of this, the feasible set is set-valued mapping, and therefore there are some difficulties also how to also solve those kind of problems. And just one example, we just in a finite dimensional space, and we have this generalized Nash equilibrium problem, and x to minus k. Also, this is actually the all players strategies and excluding this strategy of k player, and we have this n player game, and also each player has the cost function aim to minimize, and also this each player has the strategy set, and in this case, strategy set depends on strategies of other players. And okay, this is if this set is constant, then it will be reduced to a Nash equilibrium problem, and if this strategy set depends on strategies of other players, then it is called the generalized Nash equilibrium problem. And also there are many applications also of this model, how to solve, and of course we can restrict also this assumption. For instance, this cost function is convex and differentiable function, and also this strategy set is convex. Then also by introducing the following mapping, also this we have this, the component is actually gradient of each the cost function. Then also this omega is the Cartesian product of the strategy sets. Then it will be reduced to the following quasi-variational inequality, and also there is some connection between the quasi-variational inequality and also generalized Nash equilibrium problem. This is the one example, especially focusing from the practical applications perspective. Then usually also this in common is of course the generalized Nash equilibrium problem or quasi-variational inequality has infinite number of solutions, but from the numerical algorithm also sometimes it's more useful to consider some assumptions for the uniqueness of solution, existence and uniqueness. And in 1994, Knorr and Oetli investigated also the sufficient condition for existence and uniqueness, and the under Lifshitz continuous and strongly monotone mapping. And also later, the strongly monotone condition will be replaced also strongly pseudo-monotone, which is the weaker compared to the original assumption. And they investigated also this the sufficient condition for existence and uniqueness, and also the gap function. Also, if you consider variational inequality or equilibrium problem, one approach is, of course, by using the gap function, it can be reduced to the optimization problem. And if this gap function has some nice properties, for instance, differentiable function or convex function, then we can apply the well-known techniques from the numerical optimization techniques. Also, it can be used to solve the variational inequality. And the well-known approach is actually introduced by the Auslander. Auslander 1970 also is well-known. And then this approach was extended to the quasi-variational inequality by Fukushima 2007. And also we have some research on this direction is also by some German mathematicians, also from I think from Würzburg, Harms, and also I have also in this direction. I already mentioned during my PhD studies. Actually, also it is not clear and how the duality theory can be applied to construct gap function for quasi-variational inequalities. And also I visited 2016 at the University of Vienna, Professor Radovan Botz, and then also discussed and realized in also some duality results already published in 2013. And then also I have this publication, and also, and of course, number of publications also we can mention. And then most focusing on the continuous and discrete time methods. And also here I can mention some results related to also one is the extra gradient algorithms or gradient type projection, inertial projection type. And this year also during my visit at the University of Vienna also we introduced the following. Also this originally the Zeng type algorithms was investigated for variational inequalities to 2000. And also one to comment on this topic is, of course, we have one special case for quasi-variational inequalities, and this means the principal set can be, if the principal set can be expressed vector valued function plus constant set, then in this case this problem is called the moving set, which is the special case of quasi-variational inequality. And most of the publications are also devoted to this special case, or maybe only focused on the discrete algorithms. But also very interesting, recently also very ongoing research, also not only discrete, also this the continuous. Also we can consider a dynamical system and also show this existence uniqueness of solution. Okay, I will explain also here. And before I start, give some results, also some definition. Also, I already mentioned here we have first definition. If we have the mapping F, then it will be said to be L-Lifshitz continuous if this condition is true, and monotone for given mapping, monotonicity, and strongly monotonicity also. This, of course, we can give more definitions also related to the monotonicity, also this pseudo-monotonicity, but I will use those definitions. Okay, Lipschitz. Then I will mention the following result by Knorr and Oettli, 1994, and we assume. Okay, of course we can see the quasi-variational inequality, and we assume that F is L Lipschitz continuous and the rho strongly monotone on this space, and also K set value mapping with non-empty closed in convex values, and assume that also there exists L and also satisfying this condition, and then here we have this projection of set K, for this element set, and also for the parameter also we assume that this condition is true. Then all those assumptions are true. Then we can also conclude that quasi-variational inequality has a unique solution. Okay, this is the well-known result, and later the Nistero and Scrimali is also instead of this condition 1, and also it also showed also this weaker assumption. Also, the assumption can be weakened, and so I already mentioned this assumption of rho strongly monotonously also can be also replaced by strongly pseudo-monotone. So this is also some recent results also for the existence. Then mainly I will use this result for the uniqueness existence. And here we have one example from this also very. We consider the real Hilbert space, with this norm, and we can define also SF the following mapping, and here this actually this element also this each element of this vector is actually also the absolute value of sine xi. And then we can show that this mapping is alpha is greater than 1. Then we can show that this mapping is alpha plus Lipschitz continuous and alpha minus 1 strongly monotone. Additionally, we can consider this set valued mapping as follows. Okay, this is very simple construction for the set valued mapping. Example, and then we can easily verify that this set valued mapping is closed, has closed convex values for nx, and also the projection for this simple set valued mapping. Also, we can also very easy find this projection, and additionally also we can take I is 1/10, and then also this all the assumptions are true of proposition 1 true, and also we can check that we can show that this x star this companion 0 0 element is actually also the unique solution of this problem. Okay, this is the one example, and of course just I would say also this is some assumptions of proposition 1 is strong, and also we need some weak assumptions, of course. And next one is just let me mention some additional result. First one, lemma 1. We assume that the set valued mapping has non-empty closed convex values. Then x star from kx star is solution of the quasi-variational inequality if and only if. Okay, this the so-called fixed point characterization. Also, this fixed point characterization very useful also to construct also algorithm, also the projection type algorithm, and also this is the initial approach is of course very close connection. This formulation. Okay, this is fixed point characterization of the solution of the quasi-variational inequality, and here the projection onto the set can be defined as follows, as argument of this following minimization problem, and also a necessary and sufficient characterization of the projection, also known result Also, but mostly mostly it is known in case if the k is constant set. But also we can it is also shown that also in case of the set valued mapping, also this characterization is also true. Next one is also in the proof of some results. Also this result is also very usable. Also here, if the all assumptions of proposition 1 is fulfilled, then also we can show that this result is true. And by theta also we have the following, the expression of including this lambda rho is a strong limiting constantly, and L is from the Lifshitz continuity, and also this is I is also we from the proposition 1. Okay, let me mention those lemma. Now I will consider the following. I will switch to this dynamical system. We consider the following dynamical system denoted by 3, and on the left hand side we have this x dot, and here we have t for x, and the t is the continuous mapping. And then we can give this the following definition. First one is the equilibrium point for the dynamical system 3 if Tx star is equal to 0. Then equilibrium point of this the dynamical system is called stable if the following conditions are fulfilled. Okay, then stability, and then also equilibrium point of the dynamical system is called exponentially stable if the following conditions true. Okay, this is also from the dynamical system is also some known the concepts, some known concepts. Also, just before I started the just I will show this how this dynamical system of the think time also can be expressed, and also the previously one dynamical system is actually instead of there is no the yt and just one system, and then also the initial condition. But compared to the think scheme also we introduced the following think type dynamical system, and then this system also can be reduced to the dynamical system of this form. On the left hand side we have this derivative, and on the right hand side we have fx, and fx has this form. Okay, just instead of yt we can set also this projection also here in the argument, and then also we can easily obtain this form. And then first result, we assume that all for all assumptions of proposition 1 are fulfilled, and then the dynamical system of the form 4 has unique solution. Okay, this is the first result. As I already mentioned, also some projection. Okay, then there is a number of dynamical systems for quasi-variational inequalities also introduced, and compared to the existing system is actually here we use the think type. It's actually also it was not clear also how this originally this think scheme is already introduced for the variational inequality, but it is still not clear how it can be applied to the quasi-variational inequality. And also already we tried, for instance, for the special case, this moving set case, but we also tried to more generalize to obtain some generalized results, and then we have the following result in dynamical system. Second one is also then also this again we assume that all assumptions of proposition 1 fulfilled, and additionally for the parameters also the following connection is true, and also this lambda L theta is already we already here explained here theta. Okay, if this condition is true, then a dynamical system converges to the solution of quasi-variational inequality at this rate. And by the capital lambda, we use this expression. And of course, x star is the equilibrium point of the system. And okay, this is the convergence rate of this continuous model. Next result, and then also additionally is actually, as I already mentioned, the numerical scheme of Tseng is known for variational inequality, and we can also it can be expressed. Okay, also by using the continuous form, then also we obtain also this scheme. For the discrete case, also it can be expressed in this form, and here also you can see this projection of this set. And again, also we assume that all the assumptions true, and additionally between the parameters the following condition is true. Then this sequence Xn generated by Tseng type algorithm converges linearly to the unique solution of the quasi-variable. Okay, this is the it shows the linear convergence of this discrete algorithm. And also we have some analysis on the parameter analysis, also then some estimation already done. Okay, this is the also discrete system. And if you consider again the very simple example already mentioned, and then we can show the convergence behavior of this norm, okay, this norm of the error for the Tseng type, and comparing some existing algorithms, also gradient projection, extra gradient. In case of the extra gradient projection, actually you need to calculate the projection 2 times. Okay, this is also from the calculation perspective is also this number of operation will be increasing, and this is one advantage also this Tseng type algorithm. If we apply the Tseng type algorithm, and also this you can see this very similar behavior of the convergence. Also this for this example, of course we need more numerical experiment and to show to compare other algorithms. It's also this now is ongoing work research. Then also, as I already mentioned, the case with the moving set, which is also most of the algorithms is also devoted to develop to solve such case with moving set. And if the set valued mapping has this form, this A mix is the single valued mapping plus constant set, then in this case we have the quasi-variational inequality with the moving set. And for the projection also, in case of the moving set projection also, we have the following, the nice property. So of course we case non-closed convex, and then also it can be expressed. Okay, here we have just on the right hand side, here we have this vector value function, and here we have this projection of the set K onto the set K, onto the set K. Here this set is constant. And if this additionally, if this single valued mapping is beta Lipschitz continuous, then we can show that the condition 1 is fulfilled. Okay, this condition 1 means okay, this property is true. If this if the set valued mapping has the form this moving set, then after and also if the single valued mapping is beta Lipschitz continuous, then this property is true. Okay, this is also one advantage. Of course, if you consider the case of with moving set. And then we have the following result, and we assume that the set value we consider the quasi-variational inequality with moving set, and we assume that M is beta Lipschitz continuous, and additionally F is L Lipschitz continuous, strongly monotone, and K is set valued mapping with non-empty closed convex values, and for the parameters, if it's true, this condition is true, then sequence generated by Tseng's type algorithm converges linearly to the unique solution of the quasi-variational inequality. Okay, this is also in case of the moving set. Also, we as a special case, also we can show the linear convergent, and also additionally we have some analysis for the parameters. Also, this from those conditions, also we have the following estimation for the condition. Now I will switch to the second part of my talk. As I already mentioned, this my PhD thesis at Chemnitz University of Technology in Germany also deals with the construction of gap function based on the duality for construction of the gap function for variational inequalities equilibrium problem based on the, and during this time also it was still open in how this approach can be extended to the quasi-variational inequality. And here we have the definition of the gap function, the real valued function gamma, say to be gap function for this quasi-variational inequality if the following two conditions are true. The first one is the value of this function is non-negative on this set kx, and if value is equal to value at x is equal to 0, then x is solution of the quasi-variational inequality. Okay, this means by using the gap function, then we can reduce the quasi-variational inequality to the optimization problem, and if this function has some nice properties, and also if some algorithm is available, then also this more easy to find solution. The main idea of this approach is here very simple, and also first we have to rewrite the variational inequalities as optimization problem for fixed x, but if you look at this formulation, then also this principal set depends on variable x, which is the not usual optimization problem. And in this case, also this optimization problem is called actually quasi-optimization problem, and recently also some results, also more attention on this topic, quasi-optimization problem. Okay, this is the, and then okay, also we have this linear function also with respect to y, and if x is fixed, then also we have the linear function, and then also we can apply. This is also for the conjugate duality in convex optimization, also especially the research group of Professor Wanka, who is my supervisor also in Germany. Also, they have a number of publications and some applications and a number of results they achieved. And during this time, also we applied the duality results to define gap functions, and those duality results are used also to verify the properties of gap function. Okay, this is the main idea. And by using the okay, I don't go not in detail about duality results, and based on duality results by Boltz and Chetnik in 2013, the gap function for quasi-variational inequalities has been introduced in this form as negative optimal value of the dual problem. Okay, first this quasi-variational inequality can be expressed as optimization problem, and then also we define this duality. We construct the dual problems for this optimization problem, and then gap function can be defined as negative value of this optimal dual variable, and also of course this value depends on x, and then we have this function, and here this SF is for this set valued mapping, we have this lower support function. Lower support function has this form, and then the following result, and we also from this definition also we can easily calculate. It will be reduced to this form, which is the exactly gap function introduced by Fukushima for the quasi-variational inequalities. Okay, this is the one, also this connection, how those gap functions can be connected to each other. And then we can consider the mixed quasi-variational inequality and compare it to the previous case. And here we have this function p. Okay, here we have this on the left-hand side, we have this difference py and px, and finding aims to find x satisfying this condition, and then again the similar approach. Then we have the following gap function, and here we used also the conjugate function of h. Also now we have this Euclidean the finite dimensional space, and also we are using also this conjugate here in the formulation. We have this conjugate function of function h, which defined. Okay, this is also the known concept from the convex analysis. And then we have the following result, and the set valued mapping, and also again this kx non-empty closed convex values, and also this function is p is convex, and additionally the constant for fixed x for each x from Rn, then this constant qualification is fulfilled. And here we have this domain of function phi, and here we have relative interior of this set and if this constant qualification is fulfilled, then we can show that this function is gap function for mixed quasi-variational inequality. Okay, this is the result. Then here we have one remark, and of course, if we consider the constant set instead of kx constant set, then it will be reduced to mixed variational inequality, which has this form. And here we have this also this conjugate function of indicator function here. Then this it can be expressed in this form, this connection between those functions, and then we have the following function, which was investigated in 2006, and also this is also okay. Then as a special case, also we can obtain some previous results as a special case. Here we have one example. Okay, then just one example, and we have the quasi-variational inequality in moving set case, and then of course, then also in this case, then function has this form, and after the calculation, the function can be expressed in explicit form. Okay, this means also in some simple case, also in some simple examples, also we can express it in explicit form. Okay, this is the one example how can we express the function for the quasi-variational inequality. Okay, in case of the moving set. Just the last part, I will briefly explain about quasi-equilibrium problem in finite dimensional space. Okay, again we have this case set valued mapping, and the y function satisfying this condition, f is y function satisfying this condition, then the quasi-equilibrium problem has this form. Then also you can see finding x from the kx satisfying this condition, And of course, if K is constant set, then it will be reduced to a classical equilibrium problem. And instead of bifunction, we have this product, then the quasi-variational inequality, and so on. Okay, this means the more generalized form, also the which can be considered as the comprehensive the framework of some models. As I already mentioned, recently more attention on this topic, and also how some existing results can be extended to the quasi-equilibrium problem. And then I already mentioned this approach, how can we construct gap function, and then first we rewrite also this problem for fixed dx in the optimization problem, then corresponding the wall problem. And then we define the following function. And here we have this Sk is the lower support function attached to the set value mapping. And here we have also the conjugate function. And then also we can show the following result. Again, K is set valued mapping such that also this Kx non-empty closed convex. And the constant collocation is fulfilled, then we can show that this function is gap function for quasi-equilibrium problem. And on the other hand, also we can consider the minty quasi-equilibrium problem. Then also compare it to the quasi-equilibrium problem. Here we have this x is now the second variable, and the positions of the variables are changing, and also the inequality sign is also changed. And then this problem is called the minty quasi-equilibrium problem, and let us denote by KQEP and KQMEP the solution sets of the problems quasi-equilibrium problem and minty quasi-equilibrium problem. And then again, also we the similar approach. Also, this we can define the following function, and then also we use this notation gamma m. Okay, this is for the in case of the minty quasi-equilibrium problem. And then let me give the following definition: by function f said to be monotone if this property is true, and also pseudo-monotone if this is true, and also by function is said to have upper sign property at x if for any y from C if this property is true, and upper sign property. And then if f is pseudo-monotone on kx for nx from Rn, then the solution set of quasi-equilibrium problem is subset of, okay, this means any solution of the quasi-equilibrium problem is again solution of the minty quasi-equilibrium problem. And if f has upper sign property on Rn and for any x Rn, then kx is convex, then any solution of the minty quasi-equilibrium problem is also solution of the quasi-equilibrium problem. And of course, if the both properties are true, then the solution sets of quasi-equilibrium problem and minty quasi-equilibrium problem coincide. This is also one result. And if f is monotone by function, then we can show this connection between gamma m QEP and gamma QEP. Okay, this is the also result. And then I think that it is last result, and all assumptions of theorem 5 and proposition 2 and proposition 5 are fulfilled. Then also we can show that this function is gap function for quasi-equilibrium problem. Okay, this is also and then also one remark, the last remark. Okay, K is just constant subset, convex subset of Rn, and f is given function satisfying this condition. Then equilibrium problem has this form, and of course, if K is the constant set, then we have the following connection, and then we have the following result, which is the actually, I think, which is the also this investigated in 2006 for the. Okay, this means we can obtain some there's also some results as a special case for this K function. Okay, then now I have conclusion, and just as I already mentioned, I explained mainly focusing on the quasi-variational inequality. In the first part, I explained also the new approach for solving quasi-variational inequality based on Tseng's scheme, and then also the extension of the construction of K function for the quasi-variational inequality and also quasi-equilibrium problem based on duality theory. And of course, we have some ongoing research, also focusing on the relaxation parameters in the strongly pseudo-monotone case, and also numerical experiments. And also very important is also how this approach can be extended to other models. Okay, and here we have some reference also you can see in the Gauss function for equilibrium problem, Finkel duality in 2006, and we have this 2018, last year 2024, and here 2025, and here we have some this results also related to this topic. Okay, thank you for your attention.
Thank you for this beautiful talk. Is there any question? Okay. Could you be more specific about the concrete origin of the concrete motivation behind this class of optimization problems?
As I already
you gave a list of gave a list of fields, but can you give at least, let's say, one
application?
Yeah.
Yes, this as I already mentioned, this generalized, for instance, generalized Nash equilibrium problem. This is also has many applications. Also, environmental. Also, I have one publication. This actually the competition of in the rush of this in the coal market in the for instance in China, and also then we try to apply some game theoretic model, and also we need to consider some shared constraint. Then we have the generalized Nash equilibrium problem, and also this some simulation results can be also used also in the policy development of in this direction. Because of this, our country is also more focusing on the economics is very depends on the mining products, and also this is very some ongoing the copper mining or the coal mining, and this is one example. And then so we have also some environmental issues, and then those applications also can be connected to generalized Nash equilibrium problem, which is the special case also of quasi-variational inequality. And
okay, thank you.
Okay, thank you.
No more question? Okay, let's thank the speaker again.
Okay, thank you.